Okay, so we've got a particle being pulled down, connected to an elastic string. Standard technique. So we've got the length here is 1.5 L. This is 2 L. So we can use Pythagoras to get this length from there to there, which is 2 squared plus 1.5 squared square rooted. This is 2.5 L. Okay, so altogether so T, so the natural length is 3L, the stretched length, if you like, so L natural length plus X is going to be 5L, so we've got X is 2L. Okay, so we've got the tension, it's lambda times the extension, T lambda X, which is lambda times 2L, over the natural length, which is 3L, which is 2/3 lambda, or 2 lambda over 3. Note I could make this, just do one part of the string, it will just half this and half this. Okay, so I know that T cos, if I look at forces, T cos theta will be the force up, and I've got 2 of those. So resolving vertically, I've got 2T cos theta equals mg. I know cos theta, I've got a note over here, cos theta is adjacent over hypotenuse, so 2 over 2.5, or 4/5. Okay, so 2T T is 2 lambda over 3 times cos theta, which is 4/5, equals mg. Okay, this gives, rearrange that, I get lambda equals 7.5 mg over 8, or 15 mg over 16 as required. Okay, part B then, we are told that the string is stretched, so the total length is 7.8 L. So I know this must be 3.9 L, as must this. I can then work out the height, which is 3.9 L squared, take away 1.5 L squared. Okay, and then I work that out and square root it, and I get H is 3.6 L. So this is 3.6 L. Okay, now I'm going to do conservation of energy. Okay, so we've got P, and I'll call this Q for argument's sake. So at P, the only energy we've got is elastic potential energy, and that equals lambda, which already shown as 15 mg over 16. X squared, the extension, well, the string is now 7.8, natural length is 3, so it's 4.8 L squared over twice the natural length, and natural length is 3L, so this gives me 6L. Okay, now bearing in mind I could have done half, so I could have done I could have said, well, the extension in one side is only 2.4, done 2.4 L squared over double 1.5 L, and doubled it because I've got 2 strings, but that is fine. Do it in one go. It's probably a bit simpler. And then at Q, at P, sorry. Then at Q, we've got no elastic potential energy because the natural length is 3L, and it is 3L, so there's no extension. We've got kinetic energy, and we've also got gravitational potential energy, which is mg times 3.6 L, because that's the height it's raised. Okay, now we equate these two. So we've got 15 mg over 16 times 4.8 squared times L squared over 6L equals a half mv squared, 3.6 mgl. Okay, now the left hand side, rather conveniently, the L's cancelled, so to put this in the calculator, the mg and the L will leave out. 15 over 16 times 4.8 squared over 6 gives us 3.6 mgl. Clearly those two are equal, so that tells us that V equals 0, and therefore we just need a concluding statement. Therefore object comes to rest on the line AB.